All right, so for section 5.4, we want to talk about exponential functions, since in 5.3 we talked about log functions. And so, just to kind of give you an idea here what an exponential function is, so the inverse, so an exponential is just the inverse of the natural log function. Okay. So, and when I say exponentials, I mean e to the x, and e is Euler's number, and it's like 2.71828 something something something. So it's similar to pi in the way that it works. All right, but the inverse of the natural log function is e to the x. So how we can look at that is to say, so we'll say that the natural log of e to the x. So how we get rid of e to the x is by taking the natural log of it to give us x. And if we want to get rid of the natural log function, then we just raise it to a power of e to the x. Okay. So let me show you an example of that. Let's say that we have e to the x is equal to 15. All right. So how I would solve this is I would say, well, the natural log, just take the natural log of both sides. Yeah. And then, as I know from my definition up here, that I can cancel these out, quote unquote cancel there. So the natural log of e to the x just gives me x. So now I can say, well, x is equal to the natural log of 15. Plug that in the calculator, and your homework wants 3 decimal places. So we'll say that is 2.708. Okay, so I got an answer, and this is more of an algebra thing, but in case you don't remember how these functions work, this 2.708 tells me what power that I should have to plug in to x to get 15. So I could say e to the 2.708, and I would get 15 back. Okay, so that's all it is. So I solved for x. So I had an x, I solved for it, and so therefore that answer would be the power that would get me to 15. Okay. So now from a calculus standpoint, one of my favorite things about the exponential function e to the x is the derivative of e to the x is just e to the x. Okay? So the derivative of e to the x is just e to the x. Okay? Now, if we were to have something that wasn't just x in our power, so we have something u, we'll say, like a 2x plus 1 or 6x or whatever, all right, then we just use the chain rule. So the derivative of e to the u is still e to the u, but we have to multiply by the derivative of the power. Okay, so let me show you an example of that. Let's say that we have, let's do e to the 3x. Okay, and I want to take the derivative of that. All right, so my derivative is e to the 3x times, and I do the chain rule. So I take the derivative of this 3x, and which is 3, and I just multiply it on the end. So it's just using the chain rule. And so the derivative of e to the 3x is 3e to the 3x. Okay, so that's how the derivatives work for exponential functions. All right, and I'll do another example in just a moment here on when we have something that's not just a x. So let's say that we have something like y is equal to, let's do x e to the 6x. Okay, so I have a product here, so I know that I'm going to have to use the product rule. So to take the derivative of this, so I take my derivative of my first component, which derivative of x is 1, multiply it by the second component left alone, plus the first, which is x, times the derivative of e to the 6x. Okay, so my derivative for e to the 6x is e to the 6x, but my chain rule says I have to multiply by whatever's in the derivative of that exponent. So the derivative of 6x is 6. Okay, so I have e to the 6x plus 6x e to the 6x. Okay, I have an e to the 6x that I can factor out here, so I'm going to factor that out, and that leaves me with 1 plus 6x. All right, so that would be the derivative of that exponential function. Okay, so I use the product rule and the chain rule to find that derivative. Okay, so in a similar sense, integration works the same way. So if I wanted to integrate e to the x with respect to x, well, fortunately, that's just e to the x plus c. Okay, so my integral for that is just e to the x plus c. All right, and then on a similar note, if we were to have anything other than just plain old x, then my derivative, that should be du, sorry. So eu to the du, I integrate that, and I just get e to the u plus c. Okay. All right, and I can use u/du substitution to solve these. So let's do one. So let's say that I have the integral e to the 3x plus 1 dx. Okay. And I want to integrate this. Well, I'm going to have to use u/du substitution. So I'm going to let my u be 3x plus 1. So that makes my du, the derivative of 3x plus 1, be 3 dx. Well, I don't really like my 3 being right there, so I'm going to move it over by dividing and dx. So now I can replace, so now I have e to the u times 1/3 du. So I just replaced my u and my my dx there with 1/3 du. I'm going to bring the 1/3 out, and so the integral from e to u du. Well, the integral of e to the u is just eu, right, plus c. And something that you may do, and it's okay if you do, so, technically this 1/3 would distribute to both the e to the u and the c, but since c is just a generic constant, then it actually doesn't need to be multiplied by 1/3 because it's just a constant. So as far as the 1/3 part goes, all you have to multiply by 1/3 is the e to the u. All right, and then I just substitute my u back in and say, well, that's e to the 3x plus 1 over 3 plus c. Okay, and so that actually ends our section for 5.4. Okay, so it's a fairly simple concept. The examples I covered are homework type questions. I wanted to make sure I included more of those as we go forward. So this does conclude section 5.4. If you have any questions, please feel free to email me. And as always, have a great rest of your day.